Have you ever wondered why the thunder arrives after the lightning, even though they happen at the same time? Well, the answer lies in the intriguing nature of sound speed. Sound doesn't zip around at the same speed everywhere. It's a bit like us when we're swimming, jogging, or sprinting on a racetrack. Just as we move at different speeds in water, on the ground, or on a smooth track, sound too travels at different speeds depending on whether it's moving through air, water, or solids. Imagine you're a sound wave. In air, you'd move at a leisurely pace, but dive into water and you'd pick up speed. Get into a solid and you'd be a speed demon. Sound speed isn't a fixed number. It changes with the medium it travels through. It's a variable, not a constant. And that's why thunder lags behind lightning. So the speed of sound isn't the same everywhere. It's a variable, changing with the medium it travels through. Imagine you're at a concert. The sound of the music reaches your ears through the air. Now let's delve into the speed of sound in air. Picture this. The sound you're hearing is racing towards you at an astonishing speed of approximately 343 meters per second, at least when you're at sea level. But hold on a second. This speed isn't a steadfast rule. It's influenced by a couple of factors: temperature and humidity. When the air gets hotter, the molecules move faster, increasing the speed of sound. Similarly, when the air is more humid, the lighter water vapor replaces some of the heavier air molecules, which also causes the sound to travel faster. So next time you're at a concert, remember this fascinating fact. The sound of the guitar solo or the singer's high note isn't just music to your ears, it's a showcase of physics in action, traveling at around 343 meters per second through the air. Ever tried talking underwater? It's an entirely different world for sound. In this world, the speed of sound operates on a whole other level. To be precise, sound moves at a speed of approximately 1,500 meters per second in water. That's about 4 times faster than in air. Now you might be wondering, why does sound travel faster in water? The answer lies in the density of the medium. Water is denser than air, and sound waves love to travel via dense mediums. Think of it like this. The particles in water are more closely packed together, so when a sound wave hits one particle, it quickly passes the energy to the next. This rapid domino effect results in a faster propagation of sound waves. So the next time you're in a pool, remember, sound is zipping around you at about 1,500 meters per second. What about solids? How fast do you think sound travels through a metal rod? Well, prepare to be surprised because sound can zoom through a solid substance at speeds as high as 5,000 meters per second. That's right, 5,000. Now you might be wondering why sound travels so swiftly in solids. The secret lies in the structure of solid materials. Unlike gases and liquids, which have particles that are relatively spread out, the particles in solids are closely packed together. This close proximity allows sound waves to transfer energy from one particle to another rapidly, a bit like a high-speed game of dominoes. So, whether it's a steel beam in a skyscraper or a metal rod in your hands, sound waves are zipping through at incredible speeds. Next time you knock on a wooden door or tap on a glass window, remember that the sound you hear has traveled at breakneck speed. So, in a solid like a metal rod, sound is racing at a whopping 5,000 meters per second. So, we've seen how the speed of sound changes in different mediums. But what does this mean for us? To make sense of it all, let's take a quick recap. Sound, being a mechanical wave, travels at varying speeds depending on the medium. In air, it's relatively sluggish, making its way at around 760 miles per hour. Dive into water, and sound zips along at an impressive 3,352 miles per hour. And in solids like steel, it streaks by at a whopping 13,890 miles per hour. This understanding isn't just academic, it has real-world applications. For instance, engineers use this knowledge to design better acoustics in concert halls, while submarine operators rely on it to interpret sonar readings. Even music producers take into account the speed of sound to ensure the best sound quality. Understanding the speed of sound in different mediums doesn't just satisfy our curiosity, it also opens up a world of possibilities in the realm of science and technology.